Welcome back. In this session, we'll continue with the discussion on filters. Right. So in the previous session, we categorized the filters based on the frequency response of these filters. We said we can have low pass filter, we can have a band pass filter, we can have a high pass filter, we can have band stop filter, right? So we have different type of filters, and the ideal low pass filter looks like this. So the frequency characteristics of an ideal low pass filter are like this, like this. So h of omega, this is omega, and we'll say this is the cutoff frequency, meaning the frequency where pass band changes to stop band, and this is referred as pass band, and this is referred as stop band. All right. And we said, so this is ideal low pass filter. Why ideal? Because this is very difficult to have a cutoff like this. Means it's almost impossible in practice. Practically, it's very impossible to get transitions like this. Means to have a cutoff, sharp cutoff like this. You can have a cutoff that reaches almost to this. Meaning that has a sharp transition from pass band to stop band, but the order of the filter will then be very high. Order of the filter will be very high. What do you mean by order of the filter? Means number of components that you have to use will be very high. Means the hardware that will be required for this will be very high. For example, if you are designing this low pass filter using R and C components, right? So this will be a passive low pass filter. Then the number of components to achieve this sharp cutoff will be very high, which is very problematic in IC design. So the number of R and C components will be very high. Then we said we can allow a roll off between this pass band and stop band. If I say this is the stop band, like this, right? And this region between pass band and stop band is referred as transition band. This is referred as the transition. All right. Also, we see here the filter response is flat here and it is flat here. Now, can we allow some? Can we allow some? This can we allow some replacements? Can the magnitude of this filter change either in pass band, stop band, or in both? All right. Now, what I meant by this, if I talk about the low pass filter, so if I say this is the maximum magnitude, can I allow it to change between these two values? Same way, if this is the lowest value, then can I allow it to vary between this and this? What I mean by this, so can it do like this? This is the meaning of replace, right? Can it do like this, right? All right. So this is that. So this time we are allowing the replace in both pass band and stop band, and the region between those two is the transition band. Right. Now, based on this, we'll have different type of filters. For example, we have Butterworth filter. First type is the Butterworth filter. Now, Butterworth filter has flat response in both this and this. And is the both pass band and stop band are flat. Now, the second type is the Chebyshev type 1. Chebyshev type 1 filter. Right. Now, this filter allows replace in pass band. So this allows the replacing pass band. Same way there is Chebyshev type 2 filter. And this allows the replacing stop band. Here both the bands are flat. Sorry, not filter flat. So these are flat. Now in third and fourth is the elliptic type filters. This allows the replacing both pass band and stop band. Replace are present in both, and this is an example of a elliptic filter. So there are three commands. Finally, we have Bessel filters. And Bessel has maximal flat region in both. Flat region in both. And this has the largest, what's in then, see, this has a maximally flat response on both the bands. So that is identical to the Butterworth filter that is on here. If you talk about Butterworth low pass filter, what's the difference between Butterworth filter and the Bessel filter? The transition region in the Bessel filter is larger, and this gives us one advantage of a linear field that we discussed in the previous. So this has an advantage of linear field that is important for summer. All right. So we have different type of filters. Whether we allow the sharp transition, flat response in this pass band and stop band, or allow some ripples. We have different type of filters, and these filters, remember, these can be low pass, these can be high pass, these can be um, band pass. So these can be band high pass, these can be band pass, these can be band stop filters. Similarly, these can be all these types of filters. So we can have different type of filters. Now let me show these filters in MATLAB. So let me switch to MATLAB so that we are able to visualize this. First, let's see the Butterworth low pass filter in MATLAB. Right. Now let me switch to MATLAB. Okay. So let me switch to MATLAB. Alright, so this is MATLAB. Now MATLAB has an inbuilt toolbox for this filter design. That's referred as FDA tool. So if you type FDA tool, a window will pop up that looks like this. Let me share that window with you. So this is the window that pops up here, right? Now there are different menus on this. Don't worry about this. Just focus on this. There is low pass, there is high pass, there is band pass, there is band stop, there is some differentiator. Don't worry about this. And there is design method, whether you are using design method as IIR or FIR. Now first select IIR because our goal is to learn these type of filters, Butterworth, Chebyshev, elliptic and maximally flat, and other type of filter. So first let's start with Butterworth. So click on this. Then MATLAB lets you specify the order yourself, or you can allow MATLAB to select the order of this filter based on these frequency characteristics and based on these magnitude response specifications. MATLAB will select the order. So you can specify it yourself. So let me specify it, right? So the order is 10. Let me first go to order 1 filter. And then you can specify the frequency specifications in hertz, kilohertz, megahertz, or gigahertz. All right. So let's use, and you can also use the normalized range, means from 0 to 1, means the frequency range will be from 0 to 1. All right, so let me use this range because this is very easy to use, and we have to specify one characteristic, that's referred as cutoff frequency. Now the cutoff frequency must vary from 0 to 1, and let's suppose the cutoff frequency is 0.5, and if I hit design filter, this shows me the magnitude response. So I can check the magnitude response of this filter. I can check the phase response here. This is the phase response. This is both phase and this magnitude response. This is group delay. This is phase delay. This is the impulse response. Now this will give you a discrete time impulse response of this filter. Now look, this is the discrete time impulse response. This is the step response, but discrete time step response. All right, this will give you the collision zero, location of collision 0. Since there is only, this is the first order filter, there will be one pole and one zero, right? Now this will specify the filter coefficients. You can check the numerator and denominator of these coefficients are given here. All right, then you can check the other information, or you can estimate the magnitude response. All right, now let me switch to magnitude response. So this is our magnitude response. Now if you remember, I said the cutoff frequency of a filter means where the magnitude in linear scale is decreases to 70% that you have at omega equal to 0, right? So when omega equal to 0, the response must reach to 70% of that value that you have at omega equal to 0. But this is in linear scale. What about in dB scale? In dB scale, the response should be 3 dB less that you have at omega equal to 0. Now, what is the magnitude at omega equal to 0 here? The magnitude is 0 dB, right? So that means in linear scale 1. In linear scale it means the magnitude is 1. Now, so what will be the magnitude at 0.5? It should be minus 3 dB. Let's check that whether it is minus 3 dB. Yeah? Now, so let me check this whether it is at minus 3 dB at 0.5 frequency. Alright, now let me check that. This is 0.5. Now you can have a look at 0.5. The magnitude is exactly minus 3 dB. Why? Because the magnitude at omega equal to 0 is 0 dB. So the magnitude should be 3 dB less. So that means minus 3 dB. That's the meaning of 3 dB less. So let me show you this again to you. So this is the magnitude at 0.5. So this is the meaning of cutoff frequency. I hope you have got the idea. Now let me select a high pass filter. Alright, high pass filter of order 1. But again I will use the normalized frequency. Then suppose the cutoff frequency is 0.4. Then design the filter, and this is the magnitude response. Again, what should be the magnitude of this at omega equal to 0.4? It should be the value that you have at 1. The value that you have at 1 should be 70% less. In dB scale, it should be minus 3 dB. Now let me show you at 0.4. Let me show you the response. At 0.4, have a look. At 0.4, it's exactly minus 3 dB. It's actually minus 3.01 dB. Actual value is minus 3.01 dB. If you convert the linear scale to the dB scale. So I hope you have got the idea. So this is how we design a low pass and high pass Butterworth filter of order 1. Now let me switch back to low pass filter. Now let me show you band pass filter. Now in band pass we require two specifications. That is two cutoff frequencies. Let me say from 0.3 to 0.6. Okay, filter order must be right. This is the Butterworth band pass filter of order 2, and the cutoff frequency is 0.3 and 0.6. Let me show you that. What do you mean by again cutoff frequency? Is the magnitude should be dropped to minus 3 dB in dB scale. You can check at minus 3 is 3 dB, at minus 0.6 we can minus 3 dB. Have a look. So this is the frequency response of this filter. Right? So this is band pass filter. Same way you can have band stop filter. Now let me change the frequency into this. So this is 0.2. Then I will use 0.8. So have a look. This is a so first cutoff frequency is at 0.2. So let me change. So the first cutoff frequency is at 0.2. Let me check the magnitude of 0.2. At 0.2, it should be 0.3. Sorry, minus 3 dB. This is minus 3 dB. At 0.8, it's minus 3 dB. So this is a band stop filter. Now let me switch back to low pass Butterworth filter. All right. Now let's change the order to 2. We check the order 1. Let's check the order 2. So this is the order 2. Right. Now first let me show you the order 1 back. So we'll stick to. So this is a low pass filter. Now as you increase the order, what happens to the transition characteristics? The transition characteristics got sharper. You can see that this side switched to this side, got shifted toward this, the sharper transition characteristics. Now have a look at this. This does not have any ripple in either in pass band or stop band. Have a look at this. Does it have any there's ripple? No, it does not have. Right. So let's study now the impact of this filter order. So this is second order low pass filter. Now let me change the order to 20. So this is the 20 order. You can see now it has sharper characteristics and sharper transition region. So as you increase the order, let me change it to 200 now. The transition becomes more sharper. You can see. Then you can change it to 2000. You can see now it has a very sharp transition region. And its transition region becomes very small. Right? You can check the transition region is very small. I hope you have got the idea. Please check it. You can change the order further. 2500. You see, right? The transition region becomes small or sharper transition characteristics. Same way you can design a high pass filter of any order. Let's say suppose 200. With cutoff frequency 0.4. You can see this is it. These are the filter characteristics. All right. So this is the Butterworth low pass, high pass, band pass, and band stop. Please play with it and see. In the next session, we will see the Chebyshev type 1 filter. Right. Now let me show you again. Let me show you again that it doesn't have any ripple in pass band or in stop band. It does not have any ripple in pass band and stop band. That's very important. Okay, this is referred as Butterworth filter because it doesn't have any base ripple in pass band and stop band. And as you increase the order, transition region becomes very small. You can check here that go to 2500. Now it has a sharp transition region, or small transition region, and sharp roll up, right? Sharp roll up. All right. Let me end this session here. In the next session, we'll see. There is Chavisho type on